In this video, I'm going to walk you through number 3, 5, 24, 25, and the last 3 problems. So let's start with number 3. If the pressure is 1.9 atmospheres and the temperature is 25 degrees Celsius, find the new pressure when the temperature is increased to 30 degrees Celsius. Okay, so we're changing our pressure based on an increase in temperature. And so if we did our charts, our pressure started off at 1.9 atmospheres. Our initial temperature was 25 degrees Celsius. Final temperature 30. We're trying to find our second pressure based on an increase in temperature. We should know that the pressure increases because at higher temperatures, particles are moving faster and colliding more often, as well as harder against the container walls. So before we begin, you guys need to convert degrees Celsius to Kelvin, because if our temperature in Celsius doubles, our pressure will not double. It'll only double if the temperature doubles in Kelvin. So that means pressure is only directly proportional to temperature in Kelvin. So to convert Celsius to Kelvin, all you do is add 273. Okay, now we're ready to set this up. You want to start with pressure. And if our pressure is going to increase, we need to make it increase by putting the larger temperature on top and divide by a smaller number. Because when you multiply by a bigger number and divide by a smaller number, then our pressure should go up, which it does, to 1.93 atmospheres. So that would be our answer for number 3. Number 5, if we have the volume of a gas is 4 liters and the pressure is 780 millimeters of mercury, what is the new pressure of the gas if the volume decreases to 3.2 liters? All right, so let's just fill in our chart. We're only changing pressure and volume. Volume starts off at 4 liters, goes down to 3.2. And our pressure starts at 780, and we don't know what the second pressure is, the new pressure. So if volume decreases, if we're putting our particles in a smaller volume, look at how little space they have to move around. They're probably going to be colliding a lot more in this smaller space. So that means the pressure increases when our volume gets smaller. So just like the problem before, we start off with pressure. If we're trying to make our pressure increase, we need to put our larger volume on top and our smaller volume on bottom. That comes out to 975 millimeters of mercury. Now, if there was a problem where our pressure was actually supposed to decrease instead, then you would put the smaller number on top. You would multiply by the smaller number and divide by the bigger number. All right, number 24. So I forgot to put the letter B in here, but hopefully you got that. Calculate the mass of a 30 centimeter cubed sample of metal B and you should have found that the density of metal B is the slope of its line, which is 2.64 grams per centimeter cubed. So this means for every 1 centimeter cubed of metal B, it's going to have a mass of 2.64 grams. If we have 2 centimeters cubed, it's going to be twice that mass. 3 centimeters cubed would be 3 times that mass. So what they're really doing is multiplying. And if we were setting this up with dimensional analysis, you'd want to start with the number that they give you and then use your density. So your density can be written in this different way. It could also be written as 2.64 grams for every 1 centimeter cubed. And so remember, we want to put our centimeters kitty corner to each other so that they can cross cancel. So for every 2.64 grams, that occupies 1 centimeter cubed. But if we have 30 times that volume, we're going to have 30 times that mass. So you just multiply those out. Oh dear. Should get 79.2 grams of metal B. For number 25, we're kind of going the opposite way. You're given mass and you're asked to find volume. So again, metal B has a density of 2.64 grams for every 1 centimeter cubed. So for every 2.64 of that, this amount of grams is going to have a space of 1 centimeter cubed. So if we were just thinking about it conceptually, you would probably know that you have to divide these two numbers. But if you wanted to set it up the dimensional analysis route, you want your grams kitty corner to each other so that they can cross cancel, and your centimeters cubed on top, because that's what we're trying to find. So you take 50 divided by 2.64, and you should get 18.9 centimeters cubed. Right, last 3 problems. 31. You forgot about your 2-liter pop, which is about 2,000 grams, in the freezer, cooled from 25 to 0. How much energy did this release? Assume the pop is made of water. All right, so how many times have you guys done this? I definitely have. So let's circle all the information that we're given. We have 2,000 grams of mass. It cooled from 25 degrees Celsius, that's our initial temperature, to 0 degrees Celsius, and that's our final temperature. How much energy, which is Q, did this release? Assume the pop is made of water. Okay, if you're having trouble deciding which equation to use, you need to check out that flow chart that I believe I posted last Thursday on the website. And basically it says if you have a change in temperature, you're going to want to use Q equals MC delta T, where we're actually solving for Q in this instance. So you just plug and chug. 2,000 grams is your mass. Your C is the specific heat of whatever is cooling down. In this case, it's liquid water. So we want to use 4.18 joules for every gram degree Celsius. Now our delta T is the change in temperature. Its final temperature is 0, and you subtract the initial temperature, which is 25. So you'll actually get a negative number here, and that just means that it's releasing energy. So when you plug this in, 2,000 times 4.18 times negative 25, you get negative 209,000 joules. And again, that negative just means that energy is released. And since the way that they worded it, they knew that it was going to be released, you kind of just drop the negative. It's okay. So after it cools down to 0, we're assuming that this pop is going to freeze. Again, we have 2,000 grams of mass. How much energy did it release? That's our Q. So we're solving for Q when our pop freezes, freezing going from a liquid to a solid. If you have a phase change that involves a solid, you're going to want to use the equation that has the heat of fusion. In this case, it's going to be the heat of fusion of water. And so you just take our mass times 334 joules per gram, crank those numbers out, you should get 668,000 joules. The last problem. Now, there's not really any math involved. But you guys do need to know the temperatures at which water boils and condenses, as well as freezes and melts. So water boiling and condensing, going from a gas to a liquid or vice versa, always happens around 100 degrees Celsius. Freezing and melting, going from a solid to a liquid or vice versa, happens at 0 degrees Celsius. So we're just having water vapor cooling and condensing. It's starting out at 110 degrees Celsius. Now, it's not going to condense right away. It has to first cool down to the temperature at which it condenses, which is 100 degrees. And so you should have a line showing the water vapor cooling down, changing its temperature. And then once it hits 100, it's going to condense. Now, based on how this question is worded, it's okay if you stop right there, and it's also okay if you carry it on further. Now, always remember that in these curves, whenever there's a change in temperature, that's changing thermal energy, and that deals with particle motion. And whenever there's a flat line, that means the change in temperature is 0. So the temperature is not changing. So the particles remain the same speed because temperature is related to speed. So if the temperature doesn't change, the speed doesn't change. But energy is still being added. So what that energy is doing, energy is being removed over time in this case. So that removal of energy is causing the particles to gain attractions, because there was a lot of energy in a gas to keep those particles apart, but then when it forms a liquid, those particles are going to get closer together, and so they have to lose energy to do that. And that deals with phase energy.